Okay, yeah, thanks very much. And yeah, I'd like to thank organizers for realizing this very nice program, or conference, as well as the associated program. So like many of you, I was coming to KITP almost like every year until 4 years ago. Then everything, shut down, and I was isolated in Japan for a few years. So yeah, I'm very happy to come back to this very exciting place. Okay. By the way, yeah, this is from California coast 4 years ago. So the organizers wisely asked me for the title. I don't remember, several months ago. so I was optimistic and gave this title. But maybe I was too optimistic. So yeah, this is still work in progress, and I'm afraid my talk would be maybe too simple so far. But on the other hand, no, this is at the end of the long day, so probably you guys are tired. So maybe good opportunity to give a very, very simple talk. Okay. So yeah, this work is mostly based on what I have been doing with my student, Miles. So he's a second year student, grad student, but somehow my talk is also related with some other project I have been doing with Yuan Wang at IOP Beijing and his student Zilong. So I will briefly also mention about their contribution. So okay, so here in this room, everyone is basically expert, so I don't think I need to give a general introduction, but yeah, so in classical kind of magnet, if you go to very low temperature, you find some order. Then ordering usually means well, at least is if you have magnetic order, then you have spontaneous breaking of continuous symmetry, spin rotation symmetry. Then the system must be gapless because of the number Gosson mode. But as you know, we have some spin gap systems, disordered ground state due to quantum fluctuations. And those systems are, of course, interesting from our perspective. But on the other hand, in some sense, gap system is, less responsive to external perturbations. So sometimes we want to make such system gapless, which is more responsive to external perturbations. And of course, one popular way to make a gap system into gapless system is to apply magnetic field. So usually in gapped system with unique ground state is singlet, but there is let's say triplet excited state, and if you apply magnetic field, then of course this one of the triplet branch comes down, and then you have gap closing. Of course, it depends on the system whether you have first order transition here, or sometimes you have continuum of gapless excitations above this crossing. So in that case, you have second order quantum phase transition. Anyway, it of course depends on the system, but yeah, in this way we can close a gap of gapped spin system by applying magnetic field. And so in this talk, I want to focus on the 1D system. And of course, we know gapped 1D system. The famous one is Haldane gap system for integer spin chain. But of course, there are other systems as well. So if spin is half-ordered integer for this standard Heisenberg chain, of course, we have a gapless system to begin with. But if you have integer spin, then you have gapped spin chain. Then you can apply magnetic field to close the gap. And other examples are spin ladders. So you can have a spin-1 half ladders like this. And in this case, a gap system can be easily realized by having a strong rank interaction. Then you have basically a collection of dimers, which is some sense trivially gapped. But even in that system, if you have finite non-zero leg interaction, then you can apply the magnetic field. Then the system becomes a gapless, which is as non-trivial as other gapless 1D spin chains. Okay. So in 1D, as I said, you can start from gapped spin chain or spin ladder and apply magnetic field. Then you have a gap closing. Then, of course, strictly speaking, it depends on each model or system. But typically what happens is that above this critical field, you have gapless 1D quantum fluid, which is typically so-called Tomonaga-Lattinger-Rigid or Lattinger-Rigid, which is described by just a 1 plus 1D free boson field theory. So this Tomonaga-Lattinger-Rigid is very, very strong universality class, which can describe many, many gapless 1D systems. And this field-induced gapless phase of 1D magnet is one of such examples. So yeah, this also applies for spin-1 Haldane chain. So at zero field, it has Haldane gap, but you can apply magnetic field and close the gap. Then above this critical field, you have gapless Tomonaga-Lattinger-Rigid. And basically, this Tomonaga-Lattinger-Rigid is the same universal theory which describes either this field-induced gapless phase of Haldane gap phase or spin-1 half chain, which was gapless from the beginning. Although there are several differences, but basically this is a universal theory for 1D gapless spin systems. Okay, so so this was about zero temperature, but since most of the, well, basically any experiment is performed at finite temperature, we are also interested in finite temperature. Then, as you know, in 1D system with short range interaction, there is no phase transition at finite temperature. But still, even at finite temperature, you can feel the effect of this quantum phase transition at zero temperature. So this is famous diagram, which probably you have seen so many times, including Spear's textbook. And yeah, also in this case, yeah, we are interested in this quantum critical behavior. Okay, and so as this is also well known, but this particular quantum critical point and associated quantum critical behavior, that is field-induced gapped to gapless transition in 1D quantum spin system, has very simple description. That is, I don't bother writing the mathematical formula, but it's well known that spin-1 half chain or hardcore boson system can be mapped to mapped to fermion system by so-called Jordan-Wigner transformation. So in 1D, you can basically do that. Then you can describe this system as a collection of fermions, which are usually generically interacting. But this field-induced transition means that so for these particles, magnetic field acts like a chemical potential. So you are shifting the chemical potential. And field-induced transition happens exactly when this chemical potential hits zero energy. So above this critical field, you have some finite density of non-zero density of fermions. But below critical phase, in gapped phase, you have an excitation gap. So the ground state is basically given by vacuum of fermions. And when you are interested in a critical point or critical behavior around the quantum critical point, this fermion density, which corresponds to Magnon density in original spin chain language, is basically zero, around zero, very small. So in that limit, even if you start from interacting fermion model, which is a case for generic system, this effect of interaction can be ignored. So you can describe this critical point and the critical behavior in terms of free fermion. That's the idea. And of course, this has a long history. Many people applied, and again, you can find this kind of discussion in Subia's textbook. So yeah, this is very well known, but still this simple theory can have some interesting consequences. And before discussing yeah, okay, so yeah, this is another point I wanted to make is that I started from the gapped spin system, 1D spin system, like a Haldane gap chain, and then applied a magnetic field, then close a gap. Because that's usually more experimentally interesting. But you can also start from, let's say, spin 1/2 Heisenberg or XXD chain, which is gapless tomodal-Rattinger liquid to begin with. But if you apply magnetic field, a very strong magnetic field, then eventually you can polarize all the spins. Then beyond this saturation field, the system is gapped. And this critical point is basically described by the same theory. And just that starting from gapped phase, you consider Magnon or tripron, which has positive magnetic moment. But in this case, in this gapped phase is completely polarized. All spins are pointing up. So here you consider Magnon with a negative magnetic moment. That is the only difference. And otherwise, the description is basically the same. Okay. Then before going to dynamics, yeah, this is an old story, but let me quickly mention the consequence of this free fermion description of quantum critical point on thermodynamic or static property. So as I said, so you can do this Jordan-Wigner type mapping, which means that magnetization you can measure in experiment corresponds to fermion density. And as I said, we can consider free fermion system. So the fermion number at finite temperature is just given by this standard formula, the density of state times Fermi distribution. Then you integrate over energy. But so then if you recall what we learned in solid state physics, maybe undergraduate or graduate, so you can deal with this in Zomer period expansion at low temperature. Then the leading, so at zero temperature, you have some number, but leading contribution at low temperature is given by derivative of the density of the state. But in 1D, this density of state is diverging at the bottom of the band, like a 1 over square root of energy. So that means that the derivative is negative. So starting from zero temperature, if you increase the temperature, the particle number, fermion number drops as you increase the temperature. So this is a consequence of this simple free fermion picture. And in fact, not just a Zomer period expansion, but you can carry out this integral exactly, or you can express the result of integration using the polylogarithm function. So as a function of temperature, at some magnetic field above the critical field in gapless phase, the magnetization as a function of temperature should take this kind of form. So this should be universal function in the neighborhood of the quantum critical point. And as I said, if you go to very high temperature, you excite a lot of Magnons, so the number of Magnon increase. That's kind of natural. But before increasing, the Magnon number should drop. That's a bit strange behavior, but this is a consequence of this free fermion picture, and also this should be a universal function describing the neighborhood of this field-induced gap closing transition. Okay, and so we got this theory. So we try to verify for concrete models like Haldane gap chain. So basically, vertical axis is magnetization, and the horizontal axis is temperature. And as predicted by free fermion theory, actually this quantum Monte Carlo result also shows some finite magnetization at zero temperature above the critical field in gapless phase. But as you increase the temperature, first this magnetization should drop, then increase. And yeah, you can find this minimum, which is kind of universal property of this free fermion type critical point. And near the saturation, as I said, we can describe the system by same theory, but just role of the Magnon is reversed. So instead of the magnetization minimum, now we find the magnetization maximum as a function of temperature. And yeah, this magnetization minimum is proportional to the distance from the critical point. So H minus, sorry, this magnetic field minus critical value. So this is a distance from the critical point, and they should be proportional in the asymptotically in the neighborhood of the quantum critical point. And this slope is also universal number. So roughly speaking, this magnetization minimum could be identified as a crossover between gapless topological liquid and quantum critical behavior. So if you start from, well, either way, so at high temperature, the system is in quantum critical regime, but as you lower the temperature, you enter the gapless topological liquid phase, and this minimum roughly occurs at this crossover temperature. Okay. And okay, I skip this. And so yeah, after our work, so this was verified in experimentally. For example, this is some spin-1 half Heisenberg ladder, and they indeed find this magnetization minimum, and they plotted this magnetization minimum versus applied field, and yeah, again at high, as you move away from the critical point, of course they deviate, but in the neighborhood of this quantum critical point, this magnetization minimum temperature agrees with this universal slope. So it should be, but still, it's nice to see that this universal theory, simple theory works. I mentioned this. Oh, sorry, this is old story, but I mentioned this partly because we started working on dynamics of this kind of system recently. Then I looked for some difference, and then I found these papers. These papers were written for cold atoms by Jason Ho and so on. And this is theory paper, and this is experimental paper. And yeah, basically they try to describe the same critical points in the context of cold atoms. And yeah, basically the same theory, although yeah, they use this free fermion theory in very clever way to identify the quantum critical point that we didn't. But anyway, yeah, they also got this density as a function of temperature using this polylogarithm function, which is familiar to me. And yeah, apparently not aware of work. But I'm not blaming them because I too didn't notice this paper for many years. Although sometimes I join a cold atom kind of program at KITP, so that means perhaps I should come here more often. Anyway, yeah, so yeah, perhaps I should send them some friendly message. But anyway, this also shows that this simple, very, very simple theory has many applications, including cold atom, which is of course not surprising because the Hamiltonian is basically the same, but they can do other type of experiment. Anyway, so So far, so good. Sorry for spending time on non-dynamics. But now, let me discuss dynamics near this particular quantum critical point, which is described by this simple free fermion theory. So it might sound also very simple, but it's not quite, because if you are interested in dynamics of SZ, spin operator, then SZ is mapped to fermion number operator or density operator, which is fermion bilinear. So you can easily calculate the dynamical correlation function of SZ by mapping to fermion. But the dynamics of transverse component, that is Sx or Sy, is more non-trivial, because if you recall this Jordan-Wigner transformation, Sx or Sy is mapped to some fermion operator, but with this Jordan-Wigner string. So in some limit, this Jordan-Wigner string consists of infinite number of fermion operators. So it's still non-trivial object because of this non-locality. But there are some way to deal with this non-locality, which we are going to use. So yeah, this can be handled either in continuum theory, but if you want to evaluate this correlation function in concrete manner, it's useful to use some lattice model. And from now on, we are going to use spin 1/2 XY chain as a representative model to realize this field-induced gap closing or opening transition, because spin 1/2 XY chain can be mapped to free fermion. And even in this model, if you apply a sufficiently large magnetic field, you can polarize all the spins to z direction. Then you can find basically the same quantum critical point. Of course, this model is special in the sense that there is no fermion-fermion interaction to begin with. That's just a specialty of this model. And for generic model of our interest, like a Heisenberg chain, we have fermion-fermion interaction if you map to the fermion system by Jordan-Wigner. But as I emphasized, near the quantum critical point, you can forget about the fermion-fermion interaction. So in order to capture universal properties, we can just use this model. So it can be mapped to free fermion chain. But still, we have to deal with this non-local Jordan-Wigner string. And this approach was, as far as I know, for XY chain, this is a pioneering paper by Delsko and company. So they studied spin 1/2 XY chain and tried to evaluate transverse correlation function, dynamical correlation numerically, because on a finite chain, Jordan-Wigner string is still finite. And still you have a lot of operators, but you can express this Sx correlation function in terms of some Pfaffian of certain matrix. And matrix elements, each of the matrix element is given by 2-point function, which is has nice analytical expression. So you just need to evaluate this numerically, this Pfaffian. And of course, this is a numerical calculation, so you cannot really go to infinite system. But using this formulation, you can relatively easily compute dynamical correlation function for system of few hundred sites. Or, yeah, we studied basically around 500 sites, and we are not even professional numerical, expert. So maybe if you are expert, maybe you can study thousands of sites, maybe. Anyway, so using this, we try to study the this Sx dynamical correlation function as a function of this real time at the same site. So we pick up single spin, maybe in the center of the system, and just try to compute this correlation function as a function of time. near this quantum critical. So first, so we study the system in a gapless regime or topological regime at sufficiently low temperature, and so this is these dots are the numerical results obtained by this evaluating Paphian. And on the other hand, this real-time dynamical correlation function in Tomonaga-Rattinger liquid can be obtained analytically, theoretically using Tomonaga-Rattinger liquid theory because it's conformal field theory. So you first obtain the correlation function in infinite plane and then do the conformal mapping, then do analytical continuation and so on. Anyway, so this is a well-known result. So generally, this power depends on the Rattinger parameter K, but because of this free fermion nature, near the quantum critical point, this Rattinger parameter should approach 1. And also, we studied spin-1/2 XY chain, which is free fermion model. So for our particular model, K is always 1. For more general model, K can vary, but near the quantum critical point, we can set K equals 1. So anyway, this is a result for K equals 1. And this red curve is the it's a theoretical prediction for finite temperature T, but for infinitely long system. So the actual numerical computation is done for finite system of 501 sites because we wanted to study the center spin. And anyway, so for large time there is a deviation, but up to T equals to 100 something, they agree very well. Of course, they should agree, but we can verify. And the other limit is the high field regime. And then we have a finite gap induced by magnetic field. And we consider temperature sufficiently lower than this induced gap. Then basically this SX correlation function can be written in terms of S plus and S minus. And if you consider S plus S minus correlation function, this S minus just flips single spin. Then this single spin propagates as if free particle on the lattice. So basically you pick up a single particle propagator on the lattice, which can be written as in terms of Bessel function. So this J is coupling, but this J0 is a Bessel function. This is an exact result, but asymptotic form, because this particular form is probably not universal, but the large T behavior, asymptotic behavior should be universal, which we can extract. This should be universal large time behavior. Anyway, so this Bessel function is analytical prediction, which again matches very well with numerical computation on XY chain, which is, of course, they should match, but they do. So it's also interesting to consider finite temperature effect, because this Bessel function form should be exact strictly at 0 temperature, but even in a high field regime, T quite small, we are interested in finite temperature effect. And at finite temperature, there is a finite, small but finite density of thermally excited magnons. And you create magnon by spin flip S minus, but this created magnon collide with the thermally excited magnons, which are already there. So this collision induces some decoherence or decay of the signal. And actually, if you look at Sbia's quantum phase transition textbook, he discusses a semi-classical argument to derive this form. So this is the actual spin-spin dynamical correlation function, which should be written as a product of the single magnon propagator, which I introduced, and times some decoherence factor due to collision to other magnons. And he gave an explicit form of this decoherence factor, which is nice. But what Zilong and Yuan did recently is that they started from XY chain and without assuming semi-classical approximation. Yeah, of course, they have to take a low temperature limit, but starting from the first principle for correlation function of XY chain, they did derive this form. And in fact, this decorrelation factor in general is given by this integral, which agrees with Subia's expression. And also, in particular, at x equals 0, the local correlation function, this function decays exponentially, and this coherence time or decoherence time has this simple expression, which can be also derived from the analytical expression of correlation function in spin marker XY chain. Anyway, so so those are nice, but maybe most interesting is the quantum critical region spanning from this quantum critical point. And I'm running out of time. So this S plus S minus correlation function corresponds to hard core boson correlation function with this kind of Lagrangian. And again, if you look at the Subia's textbook, then because of the scaling argument, this correlation function is expected to behave like this in terms of some universal scaling function times some square root t factor. And in Subia's textbook, the asymptotic form of this universal function for large spatial separation at equal time is given using some Toeplitz determinant technique or something. But yeah, as far as I know, I couldn't find a behavior of this universal scaling function at x equals 0, but for large time. So that we try to evaluate numerically. So, okay, so this is our result. So this is just from numerical calculation of this Pfaffian at x equals 0, at the same site, Sx, Sx at the same site, but for large time t, at various different values of temperature, but they nicely collapse into the same curve if you do this scaling. So indeed, this dependence is universal function of temperature times time. And okay, so probably it's not exactly exponential, but it looks almost like linear in log-log plot. So this universal function is well approximated by this simple exponential. And this exponential decaying factor is 0.756 something times temperature times time. And you might think, okay, this is just some constant, but I think this should be universal. For example, if you consider Tomnagra-Tinja-Likit behavior, as I said, this is given by this square root of sine hyperbolic inverse. But for large time, this is just given by this exponential. And in this case, this coefficient of temperature times T is pi half, which is 1.57 or something. And this was universal. So likewise, because this is already written in terms of scaling variable, I think this number should be universal. I'm not totally sure how precise. Okay, so this error is just in our fitting. But I'm not totally sure how precise is this value, but okay, maybe 3/4 or maybe pi half is 1.57. So maybe this is actually pi quarter, 0.78. Maybe looks a little bit off from this number, but I don't know. So I wouldn't be surprised if in some mathematical paper, somebody already worked out this number exactly. But, so if you know anything, please let me know. But I think this is a universal number, and which we can extract from this Pfaffian calculation. So yeah, okay, I'm running out of time. So this has, of course, implications on NMR, and already NMR in 1D spin system has been studied by many people. And for example, in this paper, they discussed temperature dependence of the line width from scaling argument. And basically, we can confirm their analysis from topological regime to quantum critical regime. There's a smooth connection. But we need to study more about the crossover to this gapped phase. And okay, interchain effects we haven't studied yet, but we want to study. And also, yeah, perhaps it would be interesting to study nonlinear response, which Yuan and Zilong did recently. Yeah, time to stop. But anyway, so so for topological area, we found a very interesting sharp signal if you measure third order nonlinear response. So if you measure linear response in topological, the signal is kind of broad due to fractionalization. But if you measure nonlinear response, you can defocus these spin-ons to find a sharp signal. But if you go to this field-induced transition point, the dispersion is has a curvature, so this sharp signal is, I think, lost. But maybe in some other way, we might be able to find some interesting feature from nonlinear response. Okay, so to summarize, well, so as many of you probably know, but quantum critical regime for field-induced gap closing transition in one dimension is described by free fermion theory. Very simple, but it has actually many interesting applications. And in particular, this transverse spin-spin dynamical correlation function is still non-trivial. And by numerically evaluating Pathian, we find that this real-time correlation function behaves like this with some, I think, universal coefficient 0.75 or something. Yeah, thank you for your attention.
We have time for questions.
Thank you for the talk. I want to mention that the Fourier transform, the time Fourier transform of what you're showing here, has been calculated. It's in a paper 2017, us and Thierry Giamarchi, and it has also been measured in the spin ladder material with very good agreement. So essentially, it's the same function, but the Fourier transform of this.
At this quantum critical point, I see.
Sorry?
At this quantum critical point?
At the quantum critical point for a spin ladder near near closure of the gap. So and theoretically, the S of Q omega in this near the critical point was computed, from what I understand, by Karepin back in the 1990s.
Yeah, thank you. Yeah, please let me know the difference. I try to find, but so many.
Someone else here? Ah, yeah.
So, can you remind us what the set correlation function looks like? So, which one is more relevant? Let's say when you think about NMR.
Yeah, this SSX is more relevant. Yeah, sorry, I forgot to mention. Yeah, because it has smaller scaling dimension. Yeah.
More questions? So I had one question. So in this first principles expression that your colleagues had derived for the there's in the basically in this time scale there's like a e to the minus delta over t. What's delta here?
Oh, sorry. This is the gap distance from the critical point. H minus hc.
Ah, okay.
Yeah, sorry.
Yeah. Okay.
Forward.
More questions? If not, I think we should close the session for today. Let's thank Masaki and all the speakers.